The question that I have is, what are flow and equipotential lines and seepage through soil? Alright, let's talk about them. We sort of touched on the flow lines in one of the earlier videos. They're also called seepage lines. If I track the movement of a water molecule, that water molecule is going to flow along one of these flow lines. A more mathematical way of defining them is that if I take a point, the velocity vector of the water flow at that point is tangent to this flow line right there. So now what are equipotential lines? These are contours of constant head. In other words, if I take a given equipotential line, the total head on that line remains a constant. It's going to assume a certain value. But if I take a different equipotential line, the total head is constant, but it will be different from the value on this line over there. Well, while we are at it, let me also define what is called a flow net. So a flow net is basically a network of finite number of flow lines and equipotential lines, like shown over here. I won't do this here, but it can be easily shown that the flow lines and the equipotential lines are perpendicular to each other. We're going to come back and do this more later on, but just to illustrate how the flow net idea can be used to solve seepage problems, let me take this one-dimensional setup. Let's assume that this tube here is a rectangular tube, kind of goes like that. All right, I'm looking at one of the two-dimensional cross sections, and these black lines are the flow lines. So I have 5 of them drawn here, and these red lines are the equipotential line, including this one and this one. So using the principles we've talked about so far, you can very easily see that the total head is constant on this face, and it is equal to 50 centimeter, which is this distance right here. And similarly, the total head is constant on this face, and it is equal to 42 centimeters. And it can be shown that the total head will vary linearly between this face and this face. So if these equipotential lines are equally spaced, then the drop between two of the adjacent equipotential lines must be equal, right? Must be constant. And that works out to be 1 centimeter, because the difference in the total heads between these two faces is 8 centimeter, which is 50 minus 42, and I have 8 equal drops, and therefore the drop between two adjacent equipotential lines is 1 centimeter. So if you ask me for the value of the pore pressure at point G, this is how I would do it. I would first find the total head at point G. So to do that, we come from here, and the total head over here is 50 centimeters, right? So from that, I'm going to subtract 1, 2, 3, 4, 5, 6 times little delta H. That will be 6 centimeters. So 50 minus 6 is 44 centimeters. That's the total head at point G. The elevation head at point G is given as 30 centimeters. You subtract one from the other, we get the pressure head, or the piezometric head, right? So all you have to do is to multiply that by the density of water, which is 9.81 in kilonewton per meter cubed, and you get 1.37 for the pore water pressure at point G. So just by utilizing the ideas of the flow net, we were able to calculate the pore pressure at a point inside the soil domain, which is one of the common things that we do in seepage analysis. And we'll pick up on this and do a lot more of this when we do two-dimensional seepage analysis.